Hello everyone. Welcome once again to another data science related tutorial on Slidescope's Colorstick channel. And in this video we are learning about object classification or recognition with CNN in Python, which is convolutional neural network. Before starting the project, first we will understand what data set are we going to use in order to train our model for this project. So the dataset we are using is object classification CIFAR 10 dataset, which is used for computer vision. The CIFAR 10, which stands for Canadian Institute for Advanced Research 10 dataset, is one of the most popular and widely used dataset in machine learning, particularly in the field of computer vision. So here's a breakdown of what it is. Its task is object classification. The dataset size has 50,000 images for training and 10,000 images for testing. There are 10 categories of objects which we will just see. Every image that is there in the dataset has a resolution of 32 by 32 pixels, and the channels are RGB, red, green, blue, that is 3 color channels. File formats are arrays of numbers representing pixel values. And when to use CIFAR 10? It is used to practice training and testing computer vision models, to benchmark the performance of classification algorithms, and to understand and experiment with CNNs or transfer learning. Now let's get back to our example of Python. So to make the tutorial quick, we have already imported the libraries because it takes time. So just open your Google Colab. In your Google Colab new notebook, connect to an environment and import TensorFlow STF, and from TensorFlow.keras import layers and models. Then from TensorFlow.keras.datasets import CIFAR 10. So TensorFlow helps data scientists and engineers train machine learning models more efficiently. And TensorFlow.keras. Keras is a high-level API that amplifies TensorFlow's use or simplifies TensorFlow's use, making it easier to build and experiment with models. It's designed for quick development cycles and experimentation, and it is perfect for rapid prototyping. So these both libraries will help us in training our models, and our machine learning models will get trained more efficiently with the help of TensorFlow. And as you can see in Keras, when we will build CNN, so it has layers and models, and it also has these datasets. So you don't have to import it from anywhere else. From Keras datasets itself, you can import this. What we are doing is we are importing the CIFAR 10 dataset, and with the help of CIFAR 10.load data, what we are doing, we are breaking the dataset into X train and Y train, and X test and Y test. First, let's see what this dataset is. So just import matplotlib.pyplot.splt, which is default plotting library. So we are, with the help of this plotting library, we are going to convert these arrays, as we already know that the file format is in form of arrays of numbers representing pixel values, and these pixel values belong to a color. So just imagine an array. So just imagine an array like this. Here you can see in one image there are pixels. Every pixel has a color. So some, for example, this pixel has an orange color, this pixel has a white color, black color, and images are 32 by 32 pixels. So in the data set, when you will count 3, 3, 6, this is 32 by 32 pixels. So each image in the data set is 32 by 32 pixels. In each pixel there is a color, and that color is represented by a mathematical number. So consider this. Let's say we are creating a color. Let's say this color. So if one pixel is of this color, then its RGB values will be 53, 131 and 153. For white color, RGB values are 255. Okay. And for black color, it is 000. So from 000 to 255, whatever values are there for RGB, it creates a color. And that's why we are seeing this image or images. So here in the data set, we have, that is why it is called CIFAR 10. We have 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship and truck. So in this data set, because it's a supervised data set, so it says in the data set there are images, and the images are labeled as these 10 labels. So what we are going to do, we will use plt.figure. We will keep the figure size as 10 comma 10, and for I in range 25, we will create a subplot 5 comma 5. That's why in every row you will see 5 images. So this will be 5 images. So we are creating 25 images. Okay, we are not writing anything in x ticks and y ticks, and we are using grid as false. What we are doing here is we are doing plt.img show x train I. So I will take value from 0 to 25, and it will show us these 25 different images. Okay, so that's what is happening. If you will take a random number, let's say 78. So in our training data set X train, which we can see here, the training set contains 50,000 images. So we can enter any number. So if we enter a number 78, so out of the 10 given classes, this is actually some image, maybe a rabbit. Okay, and let's say 49,876, some image will be there, a ship. Okay, so uh, every number here represents an image. If you want to see what this looks like, obviously with the help of plt.image show, we will be able to convert this into image. But in this array, if you want to see what one image looks like mathematically, you can see it's this type of array, and here every pixel represents a color, like 0.09, 0.33, 0.58. So here you can see this color is the first image. Okay, so this pixel, in this pixel RGB value is this. So this is 32 pixels in one row, 32 pixels in columns, and that makes the array 32 by 32. And here you can see RGB, 9 is R, 33 is G, and 58 is B. Okay, if we'll ask ChatGPT what is RGB 93358, is very dark blue, as you can see. Here also, if you will go to very dark blue, like it will be close to, like this is 103653, so it can be. So these are some principles with the help of which we can represent a mathematical array, or you can say an array into an image. Okay, and with the help of plt.img show, we can see the data. So this is the simple data set that we are going to use. Now when we are loading the CIFAR 10 data set, as we know 50,000 images are in training, and we know that 10,000 images are in testing. So we are breaking the data set into training, X train, Y train, X test, Y test. And with the help of this particular command is if r10.load data, you will be able to put x train, y train and x test, y test. You will be able to break them. And here we have normalized pixel values to be between 0 and 1. Okay, so the pixel values will be between 0 and 1. So as you can see here, it is something that is normalized. And what they have done is we are changing every x train value into float type and dividing it by 255, because every value is between 0 to 255. When we will divide it by 255, then it will download the data. Again, it will take some time because you know it will download the data. Now we are converting the labels to one hot encoding. What we are doing here, whatever categorical labels are, so we will use tf.keras.utils to categorical. We are using ytrain, 10. So what is the meaning of this and how we are converting labels to one hot encoding? What is the purpose? Let's understand. So the line which says ytrain is equal to tf.keras.utils to categorically ytrain, 10 converts the class labels in ytrain into one hot encoded format. What is one hot encoding? One hot encoding is a technique used to represent categorical labels as binary vectors. Instead of a single label value, each class is represented as a vector where the length of vector is equal to the number of classes. So here if let's say the number of classes are 10 as we saw, the length of vector will be equal to the number of classes, and all entries in vector are 0 except for the index corresponding to the class which is set to 1. So all entries in the vector are set to 0 except to the class. So it will be like a horizontal thing. Why one hard encoding? Machine learning models, especially neural networks, work better with numerical inputs. Many loss functions, example are categorical cross entropy, require the require the target labels in one hot encoded form. One hot encoding ensures the label are in format that is compatible with the model. So let's see again what is this line doing. Let's say obviously here it is written as this. Let's say y train is 3140. Y train is an array of labels where each label is integer between 0 and 9. The class indices for CIFAR 10. Example y train is like this 3140. The function converts these integer labels into one hot encoded vectors. So it will be like this 0 0 0 1 0 0 0. So it is 3. So 0 1 2 3, and every other thing will be 0. So in instead of 3, every other thing will be 0. So that is what is written here. All entries in the vector are 0 except for the index corresponding to the class. Okay, so if you will feed this to a machine learning model, it will understand that 3 is passed. If you will feed this, it will understand 1 is passed. Like the output class is 1. Y train is output, Y is output, X is all input. So in the input we already saw there are many images, and that's what we have done. So it can take values between 0 to 10, and machine learning models which are neural network work better with numerical input. So it requires the target labels in one hot encoded form. So this is what it is. And index starts from 0. That's why it is 0. So classes are 10, but their numbers are between 0 to 10. That's why we can see at number 0, there will be some image. There is some image. What is it? A frog. Okay. So this is one image. And if you see here, these are the class names that we have defined. Okay. So now let's go back to our example. Now the labels are ready to be used with loss functions like categorical cross entropy, which compare predicted probabilities with these one hot encoded targets. When should you use this? When you are performing multi-class classification using a loss function like categorical cross entropy. So in our function, we are using two categorical. Okay. So obviously just follow our many other tutorials. You will see in upcoming tutorials we will work more with computer vision, neural networks. So you will understand this in a better way. Now just understand that we have to convert them into one hot encoded form so that we can feed it to the model. Okay. If your labels are in integer form and the model accepts them in one hot encoded form, our labels are in integer form. They are already 0, 1, 2, 3, 4. So the model that we are going to use will accept it into one hot encoded form. If you don't use this, you can use loss functions like sparse categorical cross entropy, which works directly with integer labels. So model.compile loss is equal to sparse categorical cross entropy, and we'll see them later. So if you don't want to use this one hot encoding thing, then you can use it like that. Use this way when you will create your model. So far we have converted labels to one hot encoding. What we usually do when we train a model, we train it with X train and Y train, and we test it with X test and Y test. Now in order to create the model and train with X train and Y train, the Y train needs to be in one hot encoded form because we are going to use that particular categorical cross entropy, not sparse. Okay. Now we have seen what images are there. We have seen X train, Y train, everything. Now let's work with our model. So to work with our model, we will update last dense layer for 100 classes. Okay, here we are creating a model with models.sequential, and in our CNN we are using the layers conv2d. First let's run this, then I will explain this code one by one. Let's understand this code now. Okay, so this code snippet defines a convolutional neural network CNN model using TensorFlow and Keras, which we are obviously using, and it's a simple CNN architecture typically used for image classification tasks like those in CIFAR 10, and we also have CIFAR 100 dataset, which we will see later. So as you can see, our model has these different steps. The most important step here is layers.dense 10. Activation is a softmax. 100 classes for CIFAR 100, 10 for CIFAR 10. So if you are training with CIFAR 10, use 10 here, and if you are training with 100, use 100 here. Okay. Now let's understand this code. This code snippet defines a CNN model using TensorFlow and CIFAR. First line is models.sequential. This defines a sequential model, meaning that layers will be added one after another in a linear fashion. That means the output of one layer will be the input to the next. It's a simple and common way to build a neural network, especially for tasks where the data flows in a linear sequence. Then we are using conv 2D layer. Layers.conv 2D 32, 3, 3. Activation is equal to ReLU. Input shape is 32, 32, 3. Conv 2D, this is 2D convolutional layer. That's why its name is CNN, which is the core building block for CNNs used to detect pattern in images. So you can see from previous discussions that every image has some kind of pattern. Okay, so this layer will detect, or is a core building block to detect pattern in image. Now its first argument 32, the number of filters, also called kernels, to use. Each filter detects a different feature, example edges, corners, etc. And 3 comma 3 is the size of filter. In this case, the filter is a 3 by 3 grid that will slide over the image to perform the convolutional operation. Activation is equal to ReLU. The activation function used here is rectified linear unit. It outputs the input directly if it's positive or 0 if it's negative. It introduces non-linearity to help the neural learn complex pattern. So the input shape that we have given here specifies the shape of input image. So for CIFAR 10, CIFAR 100, images are 32 by 32 pixel with 3 color channel. That's why we have this input shape. Suppose you have all images. There is another example where images are in only, let's say, one color or two color channels. So you can use that accordingly. We have max pooling 2D layer. The layers dot max pooling 2D. This is this option here. Okay. So first this, then the max pooling layer. Okay. So max pooling 2D layer has a 2 comma 2 tuple here. So the max pooling 2D, which reduces the spatial dimensions of the image. It helps reduce the number of parameters and computation in the model, as well as preventing overfitting. So this layer will help us in preventing overfitting, and also it will help us in reducing the number of parameters and computation. 2 comma 2 specifies the size of the pooling window. It reduces the dimension of the feature map by taking the maximum value from each 2 by 2 grid. Then we have the second convolutional 2D layer. Here we have 64 3 comma 3 activation is equal to ReLU. This is another convolutional layer, but it uses 64 filters and the same 3 into 3 filter size. The increase in number of filters from 32 to 64 allows the model to learn more complex and abstract features as the network deepens. So we are getting deep inside the network. Then comes the second max pooling 2D layer. Here also we are providing 2 comma 2. Another max pooling layer follows the second convolutional layer, reducing the spatial dimensions once again. Then we have the third layer, layer.convolutional 2D 64 3 comma 3. This is the same. The layer again has 64 filters and a 3 by 3 filter size. But now the model is learning increasingly abstract features at higher levels of the network. Then we have the flatten layer. This layer flattens the 2D matrix of features into 1D vector. It's necessary because the next layer, which is the dense layer, express 1D input, not a 2D matrix. So to go into the next layer, or before going into the next layer, you have to make it into 1D. For example, if the previous layer outputs a 3D tensor with a shape of batch size, height, width, channel, flattening turns into a 1D array of size, height, width, and channels. To understand this, you have to understand tensors also, which we have covered in other videos. Then there is dense layer, which is fully connected. So layer dot dense 64 comma activation is again ReLU. So dense a fully connected layer where every neuron is connected to every neuron in the previous layer. Then we have 64, the number of neurons in this layer. Activation function is ReLU again. It adds non-linearity to the model. This layer will help the model combine features extracted by convolutional layers to make a decision. And then we have the final dense layer, layers.dense 100, where activation is softmax. Dense 100, the final fully connected layer. In our case, it is 10. It has 10 neurons corresponding to 10 possible classes in CIFAR 10. This is for CIFAR 100. In CIFAR 10, you will write 10 here. And activation is softmax. The softmax activation function is used for multi-class classification. Here we have 10 different classes. It converts the output into a probability distribution over the 100 or 10 classes, meaning the model will output a vector of 100 probabilities that sum to 1. Okay. In our case, the model will output a vector. It will create a vector of 10 probabilities that sum to 1. The class with the highest probability is considered as the predicted class. So this is how the model will be selecting what is the final output. In summary, the model is a CNN designed for image classification task. It uses 3 convolutional layers, each followed by max pooling to extract features from input image. After the convolutional layer, the model flattens the features and passes them through 2 fully connected layers to make the final class prediction. The output uses softmax to generate probabilities for 10 classes in CIFAR 10. This model is a basic CNN architecture. In practice, for better performance, more advanced architectures that are ResNet, VGG, or techniques like data augmentation and dropout can be used. Now, after understanding this or getting a simple idea that in a CNN there will be layers, so these are the 3 layers, and then we are using max pooling 2D after every layer. Next thing is to compile the model. So with optimizer as Adam and loss as categorical cross entropy as we discussed earlier, we will compile the model, and the matrix that we are going to take is accuracy. Then comes the important step. This is going to take time, and here we are taking 10 epochs. That is, every time it will run for 10 times, and every time you will see accuracy will keep on increasing. We are keeping the batch size as 64 and training for X train and Y train. Remember, in our case, X train has a lowercase letter X train. In general case, you will find it as uppercase. So if you are getting some error like this, make sure that you have written it properly. So this is going to take some time, and we are running it for 10 times, and after 10 times we can say the accuracy is approximately 0.75. Then we can evaluate the model. So we will test loss and test accuracy. So with model.evaluate, you have to provide 3 arguments, that is x test, y test, and verbose is equal to 2. You will get test loss and test accuracy. Here we will find accuracy which is 70.18%. So this is final test accuracy, and loss is 0.86. Predictions, we can predict or tested values, and it will print the prediction. So these are all arrays, and these arrays are basically its predictions. Predictions will be a numpy array where each element is a vector of probabilities for the 10 classes. For CIFAR 10 we are using. You can find the predicted class by taking the argmax of the prediction. So if you will write np.argmax prediction x is equal to 1, you will get the predicted classes. So let's run our code and see the predicted classes. You can see these are the different predicted classes. Okay, and here if you will simply type length, you can see 10,000. The tested, these are the 10,000 tested predicted classes for every 10,000 test array of images. Now what we are going to do here is we will plot training and validation accuracy values, and we will plot training and validation loss values. So we will simply type plt.plot history.history.accuracy and history.history value accuracy, history.history loss and history.history value loss. So this way you can see how our training and testing model accuracy is increasing with every epoch. How is the training accuracy going and how is the testing accuracy going? Similarly, model loss. This helps in understanding how the model is learning, and if it is overfitting, that is high training accuracy but low validation accuracy. So you will understand this. Now the next step is model.save cifar 100 model.h5. So this will save our model architecture, weights and optimizer state to a file named cifar 100 model, which you can find here in your Google Colab. We ran the object classification or recognition with convolutional neural network in Python, where we, after compiling our model and testing it, evaluating it, what I did is I simply downloaded this image. Obviously we know it's a horse. Now what we did here, I uploaded it as this screenshot in my Google Colab file, and I asked Colab to convert it into 32 by 32 array, because this is something that the model will need, because all the training and testing images are given in the 32 by 32 format like this. Okay, so this is float 32. So it simply gave me this code here, and after this code you can see, so this code opened the image and resized it to 32 by 32 and created an array. The image array shape and everything it converted, and it gave us the finally an array. To confirm, what I have done here is, after reading the image, I have taken this img array as the array, because we are reshaping it to 1 comma 3 32 32 3 for model input. Obviously we will need it for model input to test it, but when I will print the array, it is showing us this image. So the same image that we used here is now converted into a 32 by 32 array, and that's what we are going to feed in the model and test. Okay, so you can see this array value. Now the model that we created, we predicted the image array, and then using the argmax we found what label was it, because that's what we discussed earlier while training the model, that predictions will be a numpy array where each element is a vector of probabilities for each of the 10 classes in CIFAR 10. You can find the predicted class by taking the argmax of the prediction. So we took the argmax of the prediction and it is outputting it as 5. Now I simply enter the prompt what are the 10 classes names from 0 to 9. So first is airplane, automobile, bird, cat, deer, dog, frog, and horse. So 0, 1, 2, 3, 4, 5. So it is predicting 5. So obviously it's a horse predicting 5. So this is what it is doing at this moment. Similarly, you can download any other image, upload it here, copy its path. So what you simply have to do, just copy its path from here and just ask collab, or I will share this code also, and this way you can test your model also. Like you can try 4 or 5 different images, or let's say 10 different images, and see how many of them is it predicting carefully. In our case, obviously the horse is, it is white, and obviously it is not appearing as clearly, but it's still, I can say it at least predicted it's a animal. So you can also try in your case and let us know what type of result did you get. Summary of the steps are: compile the model, set up the optimizer, loss function and evaluation metrics, train the model, use fit to train the model on training data, evaluate the model, assess the model's performance on the test data using evaluate, make predictions, and then visualize performance, save the model for later use. Later we are going to use this model and test it to predict some images, and we'll see if it is able to predict any image as the correct value. Like we have these 10 classes, so how close or is it able to predict these classes? This is a simple explanation of object classification or recognition with convolutional neural network in Python. So we will cover more examples with CNN and neural networks in particular, which you will learn in upcoming chapters. So please subscribe to our channel, and if you have any queries, please ask them in the comment section. If you want to get this complete code, we will leave link in the description where you will have links to these articles, these explanations and the data set. Thanks for watching the video. Have a nice day.